Okay, quick summary of what we did in class today, and just gave an extensive development of the whole thing for people who might not have been here and might want to know, but very easily, very briefly, we used the same example previously that we've got here in the briefer summary, and the examples aren't all going to be the same either. We got the v vector 2i minus 3j, the w vector 4i minus 5j. Using the Pythagorean theorem from this point to this point, we determined that the distance is 2 square root of 2. We also note that the w minus v vector is the vector 2, negative 2, so that the dot product of w minus v with w minus v is equal to, well, here's the dot product, row, column, it's 8. Same result that we had under the radical here. And this motivates the idea that the distance between two vectors is the square root of the dot product of the difference of those vectors. So that this vector is your w minus v vector, and its dot product with itself is the square of the distance between the points, so that we define the distance between, well, okay, we didn't define the distance between two vectors. What we did was we used this as motivation to define, well, yeah, we did. Okay, here's our definition of distance between two vectors. Okay, if the vectors are u and v, then we dot v minus u with itself. Now here it was w and v and not v and u, but the same idea is going to hold, and that's for any vector in Rn. It's not just confined to R2. We then define the length of a vector to be what? Well, somebody in class had the idea, well, it's just a difference between the v vector and the 0 vector, so that's a very good way to see it. That's the v minus 0 dot v minus 0 vector, which is just the v dot v, since the 0 vector, v minus the 0 vector is just v. So the length of v is v dot v. So in red we have two definitions. Length of a vector is the square root of its dot product with itself, and we call that magnitude of v, so magnitude of v, square root of v dot v. Distance between two vectors is just the magnitude of the vector that joins their tips, if they have the same initial point. And the vector joins their tips could be v minus u, it could also be u minus v, and that's not hard to prove, but we're going to define it then, distance between u and v to be the magnitude of v minus u. And this is all on account of the Pythagorean theorem, every bit of this. But the Pythagorean theorem extends into higher dimensions, so that by using the dot product, we have a single formula that applies to any number of dimensions. Now, of course, v and u would have to be in the same vector space. They would have to have the same dimension. So, as an example, what's the distance between v equals a1i plus b1j and w equals a2i plus b2j? Okay, well, writing this out carefully in terms of the definitions, definition is the magnitude of w minus v, here's our definition, is the square root of w minus v dot w minus v. That's a definition of length, dot product of the vector with itself. When we write w minus v, well, that's going to be a2i minus a1i, or a2 minus a1 times I, so the first component would be a2 minus a1. Second component, b2j minus b1j. The component is just b2 minus b1 in the j direction. So that vector is just a2 minus a1, b2 minus b1, and there's, well, I've written it out with the i's and j's here, okay? I've done the dot product, okay? So I've just written down the difference between the two vectors, written it down again with a dot. The dot product means I write this vector as a row vector, that's just a2 minus a1, b2 minus b1. Write this as a column vector, it's a2 minus a1, b2 minus b1 in columns, and that gives me a2 minus a1 squared plus b2 minus b1 quantity squared. And then I said, reconcile that with the Pythagorean theorem. And we actually did that for a specific vector over here, but in general, why is